I'm Nova.
I'm Alloy, and this is AgentStack Daily.
OpenClaw 6.6 shipped on June 12, 2026, as a security and UX release that tightens permission boundaries across transcripts and MCP style while fixing Telegram account-scoped topic routing. Today, the OpenClaw 6.6 release, Anthropic statement on the US directive suspending Fable 5 and Mythos 5, and the cautionary tale of an AI agent that bankrupted its operator during a network scan. We're also looking at an incident where a coding agent damaged Fedora systems, a trending macOS walkthrough for local agent setups, and a reported 1.8 GB memory tax on Claude desktop startup. Further down the slate, we analyze Anthropic's model naming grammar, the arrival of the Apache Burr reliability framework, Hugging Face's open-source reproduction of DeepSeek R1, and a high-signal community discussion on the DeepSeek model family.
That OpenClaw release lands at a critical time for builders shipping multi-tenant messaging agents. By moving dispatch deduplication into the SDK and hardening the permission boundaries for transcripts and session data, the maintainers are shifting safety guarantees from per-agent configurations into the platform primitives themselves. When you combine that with the news of an autonomous agent running up a massive infrastructure bill on the DN42 overlay network, it's clear that the industry is hitting a wall where prompt-level guardrails are no longer sufficient.
Exactly. We are seeing a move toward what we call the hardened runtime. Whether it's Anthropic responding to federal directives at the access control surface or developers realizing that the terminal-based AI coding agent Claude Code is essentially spinning up a full Hyper-V virtual machine for isolation, the agent-in-a-box model is getting heavier and more secure. We have a lot of mechanism-heavy news to cover, from the Apache-backed durability of Burr to the reinforcement learning pipelines in the OpenR1 repository. Let's look at the harness layer first.
The harness layer is where the theoretical capability of a model meets the messy reality of production environments. This cycle is dominated by OpenClaw 6.6, which focuses on the ingress and egress problem, how you safely ingest untrusted content from platforms like Telegram and iMessage without leaking context or breaking the session state during tool calls. For anyone wiring agents into production messaging pipelines, this release is about making sure streamed text survives a tool call and that permissions fail closed if an execution approval times out.
It's also a big week for the local agent movement. The walkthrough for setting up a local coding agent on macOS that topped Hacker News shows that builders are looking for ways to decouple their development loops from hosted backends. This isn't just about cost, it's about privacy, latency, and having a sandbox that doesn't charge you for every token while you iterate on a complex schema. When you look at the Claude desktop report, the one about the 1.8 GB Hyper-V VM, it highlights the resource cost of high-assurance isolation.
That Hyper-V requirement is a massive architectural signal. It tells us that Anthropic views the local execution of agent-generated code as a threat model that requires hardware-level virtualization, not just a software sandbox. Meanwhile, the incident on the DN42 network where an agent ran up a bankrupting bill shows what happens when you have that execution power but no financial governor. If an agent can provision compute but isn't wired into a billing API with a hard ceiling, the loop's only natural stopping point is the credit card limit.
We are also seeing the open-weight ecosystem mature with the Hugging Face Open R1 project. Reproducing the reinforcement learning loop of DeepSeek R1 is a major step toward making frontier-level reasoning transparent. We aren't just looking at the weights anymore, we're looking at the training scripts and the reward models that elicit long chain-of-thought behavior. This week is about moving from it works to how do we make it reliable, secure, and affordable.
OpenClaw 6.6, published June 12, 2026, is a security and latency release that touches almost every ingress and control surface in the runtime. The headline theme is tightened security boundaries. Transcripts, sandbox binds, host environment inheritance, MCP STIO transports, and codecs HTTP access all received dedicated hardening. This isn't just a patch, it's a structural shift in how the runtime handles sensitive payloads. For instance, the runtime now fails closed on execution approval timeouts. If a human or an automated governor doesn't respond to a request to run a command, the agent stops rather than assuming it should proceed or retry indefinitely.
That fail-closed behavior is essential for multi-tenant deployments. On the messaging side, unauthorized DM text on Telegram is now excluded from both the cache and the prompt context. This closes a long-standing data leak path where an untrusted sender could potentially poison the context of an agent shared across a group or organization. Telegram delivery also got a major overhaul. Account-scoped topics now route to the correct agent, and streamed text survives tool calls without truncation. In previous versions, a tool call could interrupt a stream and leave the user with a partial reply. 6.6 ensures the full payload is preserved.
The iMessage transport also saw a sweep of improvements, including always-on inbound restarts and durable echo markers. This makes the agent's presence in a thread much more reliable. On the connectivity side, browser and MCP support picked up existing session CDP support. This means if you have a browser window already open with a specific profile, the agent can discover and validate the WebSocket to attach to it, rather than spawning a new, isolated instance every time. It uses a streamable HTTP loopback transport that significantly reduces the overhead for local tool calls.
We should also talk about the control UI. Startup and first reply latency dropped because the runtime now caches model metadata and uses lazy loading for / commands. If you're a builder who benchmarks time to first token on a fresh session, you'll notice that the startup catalog wait has been removed. The runtime no longer stalls while it builds the full tool index. It starts the session and loads tools in the background.
Finally, provider support expanded with OpenRouter OAuth onboarding and support for Claude Fable 5 adaptive thinking. One limitation worth flagging: because the SDK now owns the dispatch deduplication for Telegram, any builder who implemented their own dedupe layer in a custom bot needs to retest their integration. You want to make sure you aren't double suppressing messages or missing legitimate payloads because the SDK and your custom logic are fighting over the same message ID. It's a cleaner architecture, but it requires a quick check of the dispatch config.
Anthropic posted a public statement addressing a U.S. government directive instructing the company to suspend access to two designated offerings, Fable 5 and Mythos 5. This appeared on Anthropic's news page and immediately became a major focal point for developers. It is a rare moment where a top-tier lab has to pull back a product not because of a roadmap change or a model deprecation, but because of an external policy directive.
The mechanics here are critical for anyone building production-grade agents. This access change is policy-mediated, not capability-mediated. This means the underlying inference infrastructure, the model weights, and the serving stack haven't necessarily changed. The gating happens at the access control surface. For a builder, the shift is binary. API calls that worked 1 hour might return an access-denied response the next. There is no SDK update or config tweak that can route around a directive like this, because the authorization is revoked at the provider layer.
This highlights a specific type of platform risk. We talk a lot about model drift or API downtime, but this is policy discontinuity. When you integrate a flagship model like Fable 5, you are inheriting the regulatory and compliance footprint of the vendor. If a government directive targets a specific endpoint, the impact cascades through your entire stack. Anthropic's statement suggests they are complying with the federal instruction, which shifts the availability for all users of these specific products.
For teams integrated with Fable 5 or Mythos 5, the immediate move is to verify which secondary models in your routing table can handle the same payload complexity. Since this isn't a technical failure, there's no fix in the code. You have to pivot the model identifier in your config to an available tier. It also raises questions about whether these suspensions are time-bound or scoped to specific regions or customer segments. Until we see more detail, the most durable signal for builders is that access to any high-capability model is a privilege that can be withdrawn by a layer above the integration stack.
A cautionary tale surfaced on Hacker News this week that every builder of autonomous agents needs to hear. An AI coding agent reportedly ran up a massive cloud infrastructure bill while attempting to scan the DN42 overlay network. DN42 is a community-run space where people experiment with BGP routing and network configurations outside the public internet. It's a playground for network engineers, but for an autonomous agent with compute provisioning tools, it's a target-rich environment that can lead to financial ruin.
The technical failure here is fascinating and terrifying. The agent was tasked with scanning or mapping the network. To do this, it apparently iterated through IP prefixes and used a tool to provision compute resources to probe each range. The problem was the lack of an external termination signal tied to cost. The agent was successful in its task, it was discovering the network, but it had no feedback loop that said each new discovery is costing you $5. Without a spending ceiling enforced at the provider's billing API or a kill switch in the agent's runtime, the loop just kept spinning.
This is a classic runaway loop but with a financial blast radius. In a traditional software environment, a runaway loop might crash a server or exhaust memory. In an agentic environment where the agent has tools that can buy things like compute, storage, or API tokens, a runaway loop exhausts the operator's credit line. The agent was simply following the prompt to map the network, and the LLM likely didn't have the context to realize that mapping meant spending.
This incident makes it clear that we need to stop treating spending caps as an afterthought. If you give an agent access to a billable cloud service, the security boundary has to live at the financial layer. You need a hard quota at the cloud provider level, not just a line in the system prompt asking the agent to be frugal. We are also seeing a need for spend rate anomaly detection. If an agent's burn rate jumps from 10 cents an hour to $10 a minute, the runtime should trigger an immediate pause for human review.
For anyone building long-running agents today, the practical move is to provision them inside scoped accounts with strict limits. Use an API proxy that can track the cost of each tool call and kill the session if it exceeds a threshold. Treat the financial kill switch as a first-class citizen of your architecture, right next to your retry logic and your timeout settings. If your agent has the power to provision, it must also have a hard limit on its budget.
There was another major incident involving an AI coding agent, this time causing unintended damage to Fedora and other Linux distributions. According to reports on LWN, an agent operating in autonomous mode with shell access executed a sequence of commands that effectively broke the host system. This has reignited the debate over how much terminal access we should give to an LLM, especially when it's running against production-adjacent systems.
The mechanism of the damage is pretty standard for a privileged agent. The agent is given a prompt, maybe to fix a dependency or install a specific tool, and it starts chaining commands. It might run a package manager update, attempt to modify a configuration in the system directory, or even remove what it perceives as a conflicting package. When these actions are performed without a human checkpoint, the agent can inadvertently delete a critical library or overwrite a boot configuration.
The issue is that most agent runtimes treat shell access as a flat capability. There is no distinction between a safe command like listing a directory or searching text and a destructive command like removing a path or uninstalling a package. Without an explicit command allow list or a dry run mode, the agent just executes whatever the model suggests. In the Fedora case, the agent likely encountered a conflict and took the most direct path to resolve it, which involved removing packages that the system actually needed.
To mitigate this, we have to look at containerization and ephemeral environments. You should never give an AI agent root access to your primary workstation. Instead, the agent should operate inside an ephemeral container or a virtual machine with read-only mounts for system directories. If the agent needs to fix a system, it should do so by generating a script or a pull request that a human can review, or by working in a snapshot of the environment that can be discarded if things go wrong.
We're also seeing a push for file system snapshots as a standard part of the agent workflow. Before an agent executes a destructive command, the runtime should take a snapshot. If the command results in a system failure, the runtime can roll back to the previous state. This incident is a wake-up call for builders. An agent with shell access is essentially a privileged user who doesn't understand the consequences of their actions. You have to build the guardrails into the transport layer, not just the prompt.
A developer walkthrough titled How to Set Up a Local Coding Agent on macOS recently gained significant traction, pulling in over 400 points on Hacker News. It's a sign that the community is hungry for self-hosted alternatives to the big hosted agent platforms. The piece walks through the specific components you need to get a coding agent running fully on Apple Silicon without sending your code or your prompts to a remote server.
The setup typically involves 3 layers. First, you have the model runtime, usually something like Alma or a similar engine that can load weights onto the Mac's unified memory. Second, you have an inference server that exposes an API, often mirroring the OpenAI or Anthropic schema. Finally, you have the harness itself, a terminal-based coding agent like Codex or a custom loop, that is configured to point its base URL at the local endpoint.
What's interesting here is how practical this has become. A year ago, running a decent-sized coding model on a laptop was an exercise in frustration. But with the latest rounds of quantization and the improvements in metal-backed inference, you can now get a very responsive agent loop on a modern MacBook Pro. The walkthrough highlights that once you point your harness at a local URL and give it a dummy API key, the tool calling loop, the part that reads files, makes edits, and runs tests, works exactly the same as it does with a hosted model.
This gives builders a low-cost sandbox. You can iterate on your prompt engineering, your tool definitions, and your agent's decision logic without burning through credits or hitting rate limits. It's also an excellent way to handle offline development or work on sensitive codebases that are restricted by data privacy policies. The walkthrough even covers how to handle the context window problem locally by being selective about which parts of the project you expose to the agent.
The limitation, of course, is that local models still don't quite match the frontier models in complex reasoning or massive refactors. But for agentic tasks like writing unit tests, fixing linting errors, or exploring a new API, the local stack is more than capable. It's becoming a routine part of the builder's workflow to have a local agent for the grunt work and only switch to a hosted model for the high-level architecture decisions.
A recent report on the Claude Code GitHub repository has sparked a lot of discussion. It turns out that Claude Desktop spawns a roughly 1.8 GB Hyper-V virtual machine every time the application starts. This happens even if the user is only using the app for a simple chat and isn't invoking any of the agentic tools that would require an isolated execution environment.
This is a classic Electron-style resource trade-off, but at the virtualization layer. The report indicates that the VM lifecycle is tied to the host process. When you open the app, it reserves that memory immediately. This is visible in the task manager and stays there as a baseline cost. The reason Anthropic is doing this is likely to provide a warm sandbox for code execution. If the user asks Claude to run a script or analyze a file using a tool, the isolated environment is already there and ready to go.
But for a developer who is already running Docker, WSL2, and maybe a local LLM, an extra 1.8 GB memory tax is a significant hit. It's not just about the RAM, it's about the thermal footprint and the overhead of managing another VM. For some users on lower memory machines, this can push the system into paging, which slows down the entire development environment. There's also the issue of nested virtualization. If you're already running inside a VM or a specialized cloud environment, the Hyper-V launch can fail or cause stability issues.
The community discussion on Hacker News suggests that users want an opt-out flag or a laser loading configuration. If I'm just using Claude to help me brainstorm a blog post, I shouldn't have to pay the 1.8 GB sandbox tax. But if I'm using it as a terminal-based AI coding agent, then the sandbox is a features, not a bug. It provides the security guarantees we talked about earlier, protecting the host system from potentially destructive agent commands.
This highlights a larger trend. AI desktop apps are becoming more like agent runtimes than chat clients. They carry a significant infrastructure footprint because they are designed to do more than just talk, they are designed to act. As a builder, you have to factor this into your capacity planning. Your development machine is no longer just running an IDE and a browser, it's running a specialized virtualization stack for your AI companions.
Independent developer Sam Wilkinson recently published an analysis titled Anthropic's Model Naming, Extrapolated. It's a deep dive into the structural patterns Anthropic uses for its model identifiers. While it might seem like a cosmetic detail, these naming strings are actually load-bearing routing keys in the inference stack. If you've ever wondered why a model is named Claude 3-5 Sonnet instead of just Sonnet, this analysis parses the grammar behind it.
The post breaks down the identifiers into tier tokens, generation codes, and version segments. For builders, this grammar is what determines how you pin a specific version of a model in your configuration. If you hardcode a string like Claude 3 Sonnet 202402229, you are pinning a specific point-in-time release. But if you use a shorter alias, you might be pointing at a rolling version that could change underneath you.
This is a versioning dependency problem. When Anthropic releases a new model, the way they name it impacts your API requests, your SDK initialization, and your CI workflows. If the grammar changes, for example, if they introduce a new adaptive tier or change the date format, it can cause silent breakage in systems that rely on string parsing to route requests or select capabilities.
The takeaway for builders is to abstract these model names behind a config layer. Don't let model strings proliferate throughout your codebase. Instead, use a parameter or a registry that maps a logical model name, like coding agent primary, to the specific physical identifier string from the vendor. This way, when Anthropic shifts their naming roadmap or releases a new version, you only have to update one line of config rather than hunting through your entire agent harness.
It's also a reminder that these strings aren't just labels, they are contracts. They imply a certain capability ceiling, a specific cost per token, and a latency profile. Understanding the extrapolated naming pattern helps you anticipate what's coming next and how to prepare your evil pipelines for the next model drop.
A new entrant in the agent framework space has caught the community's eye, Apache Burr. The full link is in the show notes, and it positions itself as a reliability-first framework. While many frameworks focus on how quickly you can build a demo, Burr is focused on the production pain points, long-running workflows, stateful execution, and failure recovery.
The core philosophy of Burr is that an agent is essentially a state machine. It separates the decision logic from the stateful infrastructure. Each step in an agentic workflow, from the initial prompt to a tool call to the final output, is a named action with its own state. This state is captured at every step and stored in a pluggable persistence backend like Postgres or SQLite.
This durable execution model changes the math for retries. In a typical agent loop, if a tool call fails or the model returns malformed JSON, you might have to restart the entire sequence from the beginning. That's expensive and slow. With Burr, you can resume from the last successful checkpoint. If the fourth tool call in a sequence of 10 fails, you only have to retry that fourth step. This is a massive win for reliability, especially when you're calling paid APIs that charge per token.
The framework also includes a built-in observability UI that lets you visualize the entire decision trace. You can see which transitions were taken, what the model's output was at each stage, and where the state was mutated. This makes debugging complex, multi-step agents much more tractable. It's also async-aware and designed to run in a server mode, allowing multiple clients to coordinate around a single agent run.
For builders who are moving past the prototype stage and into production, Burr is worth a look. It treats reliability as a first-class concern rather than an afterthought. As we move toward more autonomous and long-lived agents, having a checkpoint-based runtime becomes a requirement, not a luxury. It turns a flaky tool call from a session-ending incident into a resumable blip.
Hugging Face has open-sourced a major project called OpenR1. The goal is to provide a community-driven reproduction of the DeepSeek R1 reasoning model. This isn't just a release of weights, it's a release of the training scripts, the data pipelines, and the reward modeling components that DeepSeek used to elicit its famous chain-of-thought behavior.
This is a big deal for the open-weight ecosystem. DeepSeek R1 set a new bar for what's possible with reinforcement learning in reasoning models. But until now, the exact recipe for training such a model was largely a black box. The OpenR1 repository changes that. It building on standard Hugging Face transformers and TRL, the Transformer Reinforcement Learning Library, to mirror the RL loop that DeepSeek described in their research papers.
For builders, this lowers the barrier to studying how reasoning models are actually made. If you want to understand why a model thinks 4-5 seconds before answering, you can now look at the reward signals that were used during its training. The repo includes scripts for data preparation and evaluation, so you can see how the verifiable answers are used to steer the model's exploration.
It also opens the door for domain-specific reasoning models. If you're in a specialized field like law or medicine, you can take this OpenR1 pipeline and apply it to your own data. You can train a model to reason through complex legal documents or medical records using the same reinforcement learning principles as the frontier models. It's a shift from using a reasoning model to building a reasoning pipeline.
The repository is already attracting a lot of contributors who are porting the approach to different base models. While the compute requirements for a full reproduction are still high, the transparency provided by OpenR1 is a massive gift to the research and builder community. It's the starting point for the next generation of open, verifiable reasoning agents.
Finally, we have to talk about a high-engagement thread on Hacker News titled Notes on DeepSeek. It's a collection of empirical observations about the DeepSeek model family that has pulled in over 200 points. These kinds of threads are often where the ground truth about a model's performance and quirks emerges before it ever makes it into official documentation.
The discussion covers everything from prompt formatting gotchas to specific tokenizer behaviors. One recurring theme is the model's sensitivity to system instructions. Builders are sharing their best prompt templates for getting the most out of the reasoning mode, and there are some interesting notes on how the model handles long context retrieval compared to other frontier models.
There's also a lot of talk about reproducibility quirks. When you're running a model at the edge of its capability, small differences in the inference runtime or the quantization method can lead to different outputs. The community is effectively crowdsourcing an evaluation suite for DeepSeek, identifying where the vendor's claims hold up and where they might need a bit of prompt-level assistance.
If you're currently running DeepSeek in production, or if you're evaluating it as a cost-effective alternative to GPT-4o, this thread is required reading. It highlights the practical details that practitioners care about: latency, reliability, and how to steer the model effectively. In an industry that moves this fast, community-curated signals like this are often more valuable than the official marketing materials.
Let's wrap with the practical cue. From the OpenClaw 6.6 release, if you're running multi-tenant agents on Telegram or iMessage, the new fail-closed execution approvals and transcript hardening are essential for your security posture. You should update your runtime config to take advantage of the SDK-level deduplication, but remember to test any custom bot logic that might conflict with it.
From the Anthropic suspension story, recognize that API availability is now a policy variable. Build redundancy into your routing layer so you can pivot between model tiers or providers if an endpoint is suddenly restricted. For the DN42 bill incident, the message is clear: put a hard spending cap at the cloud provider level. Don't trust an autonomous agent with a billable API without a financial governor that can't be bypassed by a prompt.
On the local execution front, the Fedora incident reminds us that shell access is a privileged capability. Always run your coding agents in an ephemeral container or a VM. If you're on a Mac, that 1.8 GB Hyper-V tax on Claude Desktop is the price of that isolation. If you're looking for a more reliable framework for production workflows, take a look at Apache Burr. It's designed to handle the stateful, long-running agent loops that common frameworks often struggle with.
And finally, keep an eye on the OpenR1 repository. It's the blueprint for how we'll be training the next generation of reasoning agents. Whether you're building locally or on a hosted stack, the move toward transparency and reliability is the dominant theme of this cycle. We've seen a lot of growth in the harness layer this week, and that's where the next wave of agent reliability will be born.
The thread that matters for builders is not abstract. It is where authority sits. OpenClaw is moving more authority into explicit transport rules and approval behavior. Anthropic's Fable and Mythos suspension shows that providers can remove authority at the access layer. The DN42 bill story shows that cloud platforms need budget authority outside the model loop. Fedora and Claude Desktop show that local execution needs system authority boxed in by snapshots, virtual machines, and narrow commands. Burr and OpenR1 answer the same question from the other side: how do you make agent behavior durable enough to inspect, resume, and reproduce? The practical pattern is to treat every agent as a runtime with a budget, a permission surface, a recovery story, and an audit trail. That is the difference between a useful autonomous worker and a very confident process with your credentials.
For the GitHub project radar, The names to remember are Apache Burr for durable agent workflows, Hugging Face OpenR1 for transparent reasoning model reproduction, and the local macOS coding agent walkthrough for keeping small development loops private and cheap. Say the project names out loud, then use the links in the show notes and YouTube description when you want the exact repositories or source pages. The point is not to chase every framework, it is to pick the one that gives your stack a missing property, resumability, transparency, local control, or better isolation.
That's the slate for today. You can find all the links to the repositories, the releases, and the community discussions in the show notes. If you're looking for the technical deep dives or the specific config examples we mentioned, look at the show notes at tobyonfitnesstech.com.
Thanks for listening to AgentStack Daily. We'll be back soon.